Assalamualaikum. Hi, welcome to presentation of my final year project. I, Muhammad Syakran, bin Adenan, with the help from my supervisor, Professor Madya, Engineer Dr. Amir Radzi Ghani, have conducted final year project entitled Design and Analysis of UiTM Formula SAE Car Transmission System. So, what is Formula SAE? Formula SAE is a student design competition organized by SAE International, previously known as Society of Automotive Engineers SAE. The competition was started in 1980 by SAE student branch at the University of Texas at Austin. Various groups of students from universities around the world have participated in the competition. Each team of students required to design, fabricate, and test their small version of Formula type racing car based on the rules and specifications determined by the Society of Automotive Engineers (SAE). UiTM Motorsport team have joined the competition on 2016, which was held in Australia. Good old days before the COVID. Just like commercial car, the FAA car have several systems that make the car run. For example, braking system, powertrain system, and transmission system. This project focus on transmission system of UiTM FSAE car. The power output from the engine will be transferred to the wheel via the transmission system. Thus, the transmission system will exert several forces from the engine and the wheels. As you can see, the figures show the assembly of UiTM Formula SAE car in the Katya. The location of transmission system is on the rear side of the car. There are three objectives of this project. Number one, to make several designs of differential mounting for UiTM Formula SAE car. Objective number two, to perform analysis on the design. And objective number three is to determine the best design of differential mounting for UiTM Formula SAE. Moving on to scope of work, this project concentrates on differential mounting. The best design of differential mounting must be able to withstand particular forces acting on it, which I will explain later on, so stay with me. The project has been going for a year from 2020 to 2021, and the software used for creating 3D model is Katya, and for analysis is MSc Patran and MSc Nastran. Moving on to literature review, there are three types of differential that is commonly used nowadays: open differential, locking differential, and limited slip differential. The limited slip differential is the most commonly used in Formula SAE car, including UiTM Formula SAE car. As it named, the limited slip differential limit its independency of transmitting the torque on both wheels. If one wheel is on the slippery surface and the other is in the dry surface, the car can still move without skid. Next is differential mounting. According to Yozi Chonglu, the best location for differential mounting is near the engine. This is because normally the design of Formula SAE car is resolved around the engine. Thus, the area around the engine is high in strength. For the material, it is the best to use material with low density but high yield strength. Aluminum alloy is the best material for this purpose. Most of Formula SAE car use 7075 T651 aluminum alloy, including UiTM Formula SAE car. The material has 500 megapascal yield strength with density of 2810 kg/m3. For the force applied according to RGMs, there are four forces that will exert on the mounting. The forces are chain tensioning force, traction force, cornering force, and braking force. Chain tensioning force occurs during the process of transmitting the output torque from the engine to the transmission sprocket. There will be a reaction force acting on the chain sprocket against the movement of the torque. The traction force occurs on the tire during accelerate. The force to move the tire against the friction force. The traction force also occurs during deceleration of the car. Next, the cornering force is obviously occur during corner, when the weight from the inner side of the car is transferred to the outer side of the car. Lastly, Braking force occurs at the brake disc during braking. The clamping force to slow down the car will also transmitted to differential mounting since it is connected via the shaft. Let's proceed with methodology. The first step of this project is to make 3D modeling of the differential mounting. The software used in this process is CATIA because UiTM have license for the software. In this process, I have changed several parameters of the differential mounting from original design. Here is the close-up image of the transmission system, and this is the location of the differential mounting. There are two mounting that hold the differential, the left side and the right side, and the sprocket is at the center of the mounting. This is previous design of the differential mounting, left and right side. The parameter that was changed for this design are the pockets, the ribs, and additional bar at the fixed end. I will show you all the alternate design further on this video, so stay with me. The 3D models was set for aluminium as material. By setting the material, the mass of the model can be estimated in CATIA. Here is the static material properties of the aluminium alloy. The safety factor of the differential mounting is set to 2.5, so the maximum stress allowed is 200 megapascal. The next step, I will show the calculation of forces acting on the differential. The first one we will see is chain tensioning force. The small gear is driven gear, which is from the engine, and the bigger gear or sprocket is the driven gear. Torque from the engine is transferred to the differential via chain and sprocket. Chain tensioning force is reaction force acting on the tooth of the sprocket. The tension force can be calculated by finding the value of torque produced on the final sprocket. By multiplying the mass, maximum acceleration, and tire radius, we can identify the torque produced on the sprocket. The mass of UiTM Formula FSAE car is 300 kg, including driver, can reach speed of 100 km per hour from stationary in 4.5 seconds. Thus, the maximum acceleration is 2.173 meter per second. Then each tire were used for the car, which equivalent to 254 mm. From this data, we can get the torque produced on the sprocket is 471.383 Nm. Then divide the torque with the radius of the sprocket, which is 120 mm, to get the value of tensioning force. Since there is two differential mounting that will support the tensioning force, the force acting on each mounting need to be calculated by using summation of moment. Referring to the free body diagram, by using the equation of summation of moment at right mounting is equal to 0, we can get force acting on left mounting, which is 2787.456 Newton. The same equation can be used to find left mounting force, which is 1132.404 Newton. The next force is traction force. Traction force is force created on the tire during acceleration or deceleration. As the figure shows, the amount of traction a tire can provide is related to the normal force it encounters. By using the equation, which was derived from summation of forces and moment, the maximum possible traction force the rear wheels be able to generate can be determined in the acceleration maneuver. The coefficient of friction is assumed to be 0.7 by inserting the value of mass, gravity, acceleration, distance between center of gravity and front wheel, rear wheel, and ground. The acceleration force is 1112 Newton. To find the acceleration force, the H sign becomes negative. The result will be 880.73 Newton. The third force that the mounting will see is cornering force. When cornering, the wheel not only subjected to vertical force but also lateral force. The resisting force occurs against the lateral force to avoid the car from skidding is known as cornering force. Its magnitude is equal to the lateral force but acts on the opposite direction. The figure shows the simplified force acting on the wheel during cornering. By calculating the normal force acting on the wheel, the lateral force can be found. By using summation of moment at the right tire, where on the FBD tire 3, we can determine the normal force on left wheel. Note that the equation here is when the car taking right turn, and then we multiply the value with coefficient of friction to get lateral force 761.997 Newton. The force acting on the outer tire can be calculated in the same way. The outer tires will create higher force than the inner tire due to weight transfer. The force at the right tire is 1298.123 Newton. Lastly, the braking force. Force occurs when the brake caliper apply clamping force to the brake disc to slow down the car. The maximum braking force applied will be able to solve completely the UiTM FSAE car from 80 km per hour in 3.24 seconds. This calculation has been made by braking system team, thus it will not show in here. The value of braking force is 2057.572 Newton. After determining the forces, we are ready to perform analysis on the model. MSc Patran and MSc Nastran was used to study the stress occurred on the model when the force are applied. I will go through the step in using this software. First, upload the 3D model in CATIA format to MSc Patran, then set the material properties for the model. Like I said before, the material used for the mounting is 7075T651 aluminum alloy, and the model was set as solid. Then, mesh the model. Theoretically, the smaller the mesh size, the accurate the result. Since I'm using student version of the software, the number of elements and nodes are limited. Thus, the mesh size used is 5 mm. Next, forces calculated before can be applied to the FE model. I choose deceleration force instead of acceleration force to illustrate the braking situation. This is the application region of chain tensioning force, braking force, and deceleration, and this is the application region for coronary force. Now, the model ready to analyze. Now the analysis is done. Let us see the result and discuss it. Before we can see the result of analysis, let me show you the result of the alternate design of the differential mounting. To ease the explanation process, let's name the design. Design 1 is for the previous or original design. This is design 2. It looks similar with design 1, but it's not. The pocket here at the fixed end is not cut through. It's solid here with thickness of 10 mm. Note that the thickness of left side and right side mounting is 20 mm and 15 mm. This is design 3. I added a bar at the fixed end for design 3. This design was inspired by Tony Scaffold. The parameter of the pockets also changed. Ribs are removed. By doing this, the mass of mounting can be reduced. And lastly, design 4. I removed the bar from the design 3 and increased the angle at this area. This will be because this area will be the critical area. The static linear analysis was performed on all of the design. Note that the stress result will be shown in megapascal. There are similarity in the analysis result where the stress is concentrated on this area of the model. For design 1, the maximum stress is 303 megapascal for the left side and 301 megapascal for right side. For design 2, the maximum stress is 223 megapascal and 253 megapascal for left and right side respectively. The stress is lower than design 1 due to the availability of solid or more support at the fixed end. However, this will increase in mass. For design 3, the maximum stress is 229 megapascal for left side and 312 megapascal for right side. It seems that the additional bar on the mounting does not help in reducing the stress value. However, the removal of the ribs is not increasing stress. Lastly, for design 4, the maximum stress is 149 megapascal for left side and 127 megapascal for right side. In this design, the stress at this area is more evenly distributed. The stress is not concentrated on one point. This is good to increase the lifespan of the mounting. The table here shows the max stress on each design. The right mounting happened to see high stress due to its thickness is smaller than the left mounting, and it can be seen that design 4 have the lowest in maximum stress. The difference in the stress for left and right mounting for design 3 is high due to the mesh on the model. The mesh is not very clean on certain area, and it cannot be fixed due to limitation of student version software. Now, let's look at comparison of stress and mass of each design. I choose design 1 as the datum because it is the original design of the mounting. As we can see, design 4 offers the most reduction on maximum stress, which is 57.8%. However, design 3 shows the least efficient design, which the maximum stress is increased by 2.79%. Design 4 also showed that it's not just contributing in minimizing the stress, it also contributes in reducing mass up to 17.92%. So, in conclusion, this project successfully discovered the best option for differential mounting among the 4 tested designs, which is design 4. This is because design 4 have the least maximum stress occur on it, which is 149 megapascal and 127 megapascal for left and side respectively. The design also reduced the mass by 17%. That will be the end of my presentation. Any question, please contact me. I hope you have a great day. Thank you. Assalamualaikum.